Hello, everyone, and welcome to the National Space Academy Takeover. We are taking over the National Space Centre's social media channels all of this week to host Q&A sessions with interesting people from the space sector. My name is Kieran, and I'm the General Manager at the National Space Academy, and I'm one of the hosts for this Takeover week. And right now, I am joined by a really interesting guest. I am joined by Dr. Abigail Frost of KU Leuven. She may have to correct my pronunciation. And she is a researcher working on understanding stars, and we're going to hear a bit more about that in a moment. So hi, Abigail, how are you?
Hi, great to see you. Great to be here. I'm good, thank you. I'm looking forward to listening to some questions.
Yeah. So could you tell everyone where in the world you are and if I pronounced it right?
Yeah, I am in Leuven in Belgium. You did very well with the pronunciation. I also sometimes worry about how I'm saying it. Yeah, and I've been working here as a postdoctoral researcher for about a year. But yeah, originally from the UK, as you can probably tell. So.
Yeah, I was going to say it's not a Belgian accent, but maybe you'll acquire one over your time there. Abigail, if it would be really good to start if you could, by way of introduction to people watching, maybe just explain a bit about your background and the kind of work that you do.
Cool. I have a few slides if I could share those.
Yeah, great.
And yeah, I will do exactly that. So, right, I hope you can see my screen okay.
Yep.
Is that all good? Awesome. Well, yeah, so I'd just like to tell you a little bit to get started about my journey to working into astrophysics. So it all kind of started for me at school. I became quite interested in space when I was around 13 years old. And so when I got to A-level, I decided that I would like to study physics in particular, so I could study astronomy eventually. And so I studied physics, maths, and geography in my kind of sixth form years at A-level. And after that, I went on to study for my undergraduate degree at the University of Exeter. And I did what we call an integrated master's degree. So I basically spent 4 years learning about physics and astrophysics, and then got my master's degree. After that, I decided that I wanted to continue working in physics and astronomy, and particularly in astrophysics. So I applied for a PhD position and did my PhD in astrophysics at University of Leeds. And this was really great because I finally got like the first taste of like professional researcher. So like, you know, collaborating with people, going to conferences, sharing my work, discussing astrophysics with other people in the field. And yeah, this photo is a picture of me at like an excursion at one of these conferences. And yeah, I decided I would like to continue working in research, continue working in studying space. And that brought me to where I am now, where I am currently working as a postdoctoral researcher in astrophysics in Belgium. And this is my first job working within astrophysics professionally. So what exactly do I do as an astrophysicist? Well, I'm an observational astrophysicist. I'm an astronomer. So I use data from telescopes to investigate stars and where they come from. In particular, I used the Very Large Telescope and Interferometer, which is one of the most powerful observatories in the world in Chile, which I've had the opportunity to visit and to observe with in person. And I also observe now, during my current job, with the Mercator telescope, which is in La Palma in the Canary Islands, just off Africa. But what do I use these telescopes for? Well, my research focuses particularly on what we call massive stars. And massive stars are stars which are at least 8 times as big as our sun. And our sun is what we call a low mass star, and it lives a kind of very different life to a star that is a massive star. Massive stars go through completely different phases. They form supernovae explosions, they form black holes, whereas stars like our sun can't do that. And I want to understand what is it that kind of makes massive stars behave in this different way, where do they come from, and how do they form these huge events which shape our universe. And so I investigate massive stars in 2 ways. The first way that I do this is by looking at how they form. Now, in the background here, you can see what we call a nebulae, and this is a massive cloud of dust and gas. And this dust and gas is what all stars in the universe are made out of. And so if we zoom in on a kind of small compressed region of this nebulae, this is where stars are forming. And what I like to do is I like to zoom in with telescopes and look at the material that is forming massive stars. And this is just an artist's impression, but we think from observations that we have these disks that are feeding material in, and in particular, I like studying those disks. The other thing I like to study about massive stars is how they exist in pairs or in groups, because most stars we think are not like the sun. The star formed by itself and has its planets around it, but we think most stars, especially massive stars, actually form in pairs or in bigger groups. And I'd like to study how they get into these pairs or groups, and B, how the fact that they are in these pairs, how that affects their evolution. So we know that massive stars can eventually, if they grow very big and they're in a close binary system, they can eventually touch, and that has huge consequences for how they then continue to evolve. In the top right, you can see a beautiful simulation that's been done showing two stars merging. So we have two stars merging into a single star, and loads of material being thrown out in these beautiful spirals. And eventually, if the two stars in a binary system both form black holes, those black holes can then merge and cause these huge gravitational wave events. And so basically, I want to try and understand the nature of binaries, where they come from, and how they affect stars' evolution. So yeah, I think that kind of wraps up me and what I do. So now I'd love to take any questions.
Yeah, that's so interesting. So you said something there that kind of blew my mind a little bit. And I have got questions from students, which I am going to ask, but my prerogative to ask a few of my own first. You said that most stars form in binaries, or that so I always thought binaries were the exception, like they were an exceptional, that most star systems had one star like our sun. Is that not the case?
Yeah, so to clarify, for massive stars, we think that basically all of them form in pairs, or in even higher order groups, so maybe 3, 4, 5. We're detecting loads of kinds of systems like this. So yeah, it seems to be very, very common for at least the massive stars. And we do think that there are more binaries than we thought around low mass stars as well, but it's much more of a thing for massive stars.
All right, okay. So there's something about massive stars that makes it more likely that they'll be part of multiple systems. And you just said that up to 5, like what's the maximum number of grouping of stars that you found together?
So within my work, the highest that I found is a sextuple, so 6.
So six stars just hanging out together, presumably all multiple orbits together. That's,
yeah, or orbiting around each other. Yeah,
like a dance almost. That's wild. Well, that's just my head has exploded. That's really interesting. And are there any stars that people do stargazing with the naked eye? It was great to see the picture of the telescopes that you work with, and you can see why they call very large telescope. But are there any stars we can see with the naked eye that are binaries? Because we wouldn't know, I guess, if we're just looking up at the night sky.
Yeah, so I believe, if I remember correctly, that, well, I mean, basically the likelihood of you looking at least a massive star and it being a binary is quite high. But you wouldn't be able to resolve it with your eye, because obviously these stars are so close together and the eye is much less powerful than a telescope, for example. But yeah, I think there are, within the Orion constellation, if you can pick that out in the winter sky, highlighted by the 3 stars in the middle of Orion's belt, if you look out for that, then within the shoulders and knees of Orion, I think there are a couple of multiple massive systems. I think there is one star that will dominate, and I think Betelgeuse is a single star, which is kind of the reddest star in Orion, but I think there are in the kind of the bow of Orion, if I think correctly, then
Okay.
yeah, there are massive stars floating around. So while you can't resolve them with your eye, yeah, you can. They're definitely out there.
That's great. So I'm just going to repeat that a second, because a couple of things, because we had a couple of little glitches, and I will say for anyone viewing, we've had a few, but Dr. Frost has come back every time. So if we miss anything, I'll ask for clarification. But so some of the stars that we look at in the night sky with our eyes, we can't resolve them, but they're just one point of light to us, but they are sometimes actually massive star systems, and even in familiar constellations. That is amazing. I've really learned something here. So this week with the Takeover Week, we've got a theme of talking about careers. So I would love to keep quizzing you about stars, and maybe we will talk about that a bit. But you talked a bit about your background, and it sounds like you always knew that you wanted to work in this area. Is that true, or is that something that you found out as you went along?
So I think I'd always been interested in space since I was quite young. I think I wanted to be an astronaut when I was younger, and then I had to kind of like switch when I got into senior school, because like I hadn't really considered studying like the universe as like a career, like, because you imagine an astronaut as a job, but you don't imagine being an astrophysicist as a job when you're younger. And then kind of when I found out that was an option, I was like, okay, well, that sounds really interesting, because I enjoy like studying and finding the details of these things. So it seemed like a nice way to do it. So that's when I kind of thought about studying at university and then eventually going into a career in research.
And it sounds like you're still very much enjoying it. One of our students has asked, this is Casey, she's asked, how competitive is the field of astrophysics? Is it a competitive field? Do you feel competition with other researchers? Is that something you would say, or is it a bit more of a welcoming community?
We've just got, like any kind of, if you're applying for any position, there is an element of competition. Oh, can you hear me all right?
Yes, yes, you're back. Oh, yes, you're back. I can see that.
Cool. Yeah, so cool. Yeah, there is an element of competition in that, you know, there's only so many PhD places and there's only, you know, different opportunities right at different times. But I think that's the same as any other job. When it comes to research itself, there can be groups working on similar things which are kind of in competition, but also, you know, it just means that there's all sorts of people to work with. So collaboration, I think, is really, I think that's a more, that's a more kind of common feeling within astrophysics. You know, great science is done by working together in groups and working with other people. And so that is really like a common undercurrent of astrophysics and how we do it. So yeah, I think it's, but like every time I go to a conference, every time I've gone to any kind of big meeting, I've found everyone is usually very welcoming, especially if you're an early career researcher. Everyone wants to just kind of find out about what you're doing and make you feel involved. And yeah, I've always had a good experience. So
that's great. That's good to hear. Because yeah, I think for young people, they don't, the role of a researcher is something that maybe they won't, unless you know someone in your family, you don't necessarily know what it involves. And but you are doing your postdoc now overseas, and is that something that you always wanted to do, or when you looked at opportunities so it sounds, yeah, something you always wanted to do?
Yeah, I think it's one of the things that kind of drew me to a job in research as well, because there's so many good opportunities to live in a completely different place for a few years, you know what I mean? And like, again, if you're an observer, like there's opportunities to go to work at telescopes, to visit telescopes. And when you go around for conferences, there's also that element of kind of seeing a new place. And yeah, I really like the opportunities I have to live in different places, to see different places. And I think, yeah, it's one of my favorite things. It's exciting to think where I might end up next.
So is that the kind of spirit of adventure that you've got about? It sounds a bit like your inner astronaut as well, that kind of explorer, adventurer, wanting to go and see these places. And just mentioning on the offhand, in case you probably already know, but ESA's next intake for astronauts, they are opening applications in March. I'm not going to put you on the spot and ask if you're applying, but I do wonder if it might appeal to people like you who have always had that interest. So where you just mentioned about going and seeing some of these, working on some of these large telescopes, Earth-based telescopes. So where are they? Very Large Telescope is one of the ones that I remember you mentioned. Whereabouts have you been to work there?
Yeah, so there's quite a few in Chile, which is where the VLT is, or the Very Large Telescope is. And the reason that we build, or we like building telescopes in the Chilean desert, is because it's the driest desert in the world. And if you're observing in the optical or in the infrared wavelengths, then water can really affect your observations. So the drier the sky, the better. And also dry sky means less clouds, which is good. And yeah, so it's just a really great place to be doing observing. And also there's one of the most powerful submillimeter telescopes. ALMA is also out in that desert. It's a really great environment for all kinds of stargazing.
Yes, we've definitely done stargazing visits outside of the National Space Center on cloudy nights, and it's, you know, especially when something dramatic is happening that people want to see in the night sky, it can be a bit of a challenge. So you'll be looking at, so is the kind of data that you get back from the telescopes, is it imagery or is it something else? Because you showed those images and it's a really nice way to help us kind of visualize it in our minds, but I wonder if that's what you actually see.
Yeah, different. Yeah. So I use a technique called interferometry, which is, yeah, not imaging. Interferometry is essentially kind of like a little cheat, if you like. So instead of using one telescope to get an image, you combine the signals from lots of different telescopes and combine them all together to get an even bigger view. Well, again, it's like you're mimicking a very large telescope by using smaller telescopes at big distances. And the data that you get isn't a pretty image. You have to post-process it and then kind of interpret it very differently to how you would just look at an image. But it really allows you to kind of look at these tiny details in these star forming regions or around massive stars. So it's really, really useful. But that's the kind of stuff that I work with.
Okay, cool. That's answered my question on that, but it leads to another question, which is how do you go through that data? What do you have to do to turn that data from all of these telescopes into something that you can then present as your research?
Okay, so this is a very good question. I'm trying to think about the best way to explain. So you don't get an image, you actually get what we call interferometric observables, and they tell us about kind of, so if you imagine you're getting like a wave from each of your telescopes, and then we combine the waves together, and then those waves interfere, and you get some kind of like fringe pattern, an overlaid pattern of all these different wiggly waves. And from the size of those waves, we get information about kind of the shape, the extent of the object that we're looking at. And depending on how well those waves line up, we get information about the symmetry of the source. And so we use that to get a picture or an idea of what we're looking at. So if we have a disk, or if we have two stars, or if we have something else. So yeah.
Right. Okay. So yeah, so you end up with a kind of, it's like a pattern, I guess, of where you've got the signal kind of interfering with each other. So you've got gaps and patterns, and then each of them is, you can try and find distinctive patterns that will tell you. So that's quite a lot. And does it involve, I imagine it involves computer programming or something along those lines to try and analyze that data? Is that right to say?
Yeah, completely. So one way that we kind of put a picture, like a mental picture, if you like, to this data is that we do modeling. So one kind of modeling is geometric modeling. So you put together a kind of a simple picture of your source, and then you kind of compare the kind of fake observables from that model to what we actually get. And then if they match up, we know that what we're looking at matches this model or this picture that we have, and then we understand better the nature of the source that we're looking at.
Okay, all right. And so in your research so far, have you found, I guess you said about star formation and about the massive stars, and am I right in thinking we don't really know why some stars are more massive than others? Is that fair to say?
So we understand that massive stars form out of bigger areas of dust and gas, but why they are able to get to the sizes that they do, given what we traditionally have understood about star formation physics, had been a question for a long time. And while we are kind of seeing similarities between the formation of low mass stars and high mass stars, which shows that they are forming in similar ways to some extent, we still don't understand exactly how massive forming stars are gaining their mass. We haven't directly observed this, for example, and we still are trying to work out, okay, so we think that
oh, hang on a second, Abigail.
The mass, do they build up like?
You froze for me a moment there. So you were just saying about how we understand stars forming, the massive stars. Sorry to ask you to repeat.
Yeah. No, it's okay. Let me rewind. So yeah, so we know that the biggest stars form from the biggest clouds of material, but for a long time we didn't understand how you could compress all of that kind of mass together without the kind of heat of the forming star just blowing it away again. So it was how the massive stars kind of gained all that matter was a question for a long time. And also in terms of, we know that stars like our sun, we think that stars like our sun have these disks of material around them, and they help to form planets around stars. But for massive stars, they form much quicker, and we don't know whether they have time to do the same things in their disks. So trying to work out how that disk relates to the star, whether it's helping give it mass, whether they have time to form any interesting structures, these are all things that we still need to work out in terms of the final journey to becoming the star. So there's lots of open questions, which is,
right.
I guess,
So
why I have a job,
that sounds like,
which is nice.
yeah, that sounds like a whole lot of different areas of research to look at, because when you talk about planets as well, and I remember, I don't want to give away my age too much, but I remember when I was younger, the real prevalent belief that for most people that the solar system was unique, that planets around the sun was the only place we knew of it was here. And now from people like yourself and other researchers and missions like the Kepler mission, very famously, exoplanets are thought to, so that's planets around other stars, are thought to be more the norm rather than the exception. And so you mentioned your six-star system. Would a system with that many stars have planets?
Well, yeah, this is a question. I think it depends a lot on time. It depends if, and also on dynamics. So it depends whether the presence of so many stars in the system, like has that, because that will disrupt any kind of disky material, any surrounding material, any that might be forming. So like, will it disrupt it to the point where you can't form planets around any of the stars, or will it not? That's a question that we need to address. Yeah, or if, because it's such a complex system, if there were any planets that managed to form, would they, could they be thrown out of the system through dynamical interaction? There's loads of different questions that we need to address. But I mean, since these high order systems are kind of very rare, or rarer than, binaries at least, we still have some work to do to work that out. But potentially lots of very cool stuff could happen. And so which is exciting, because if we get to work it well.
And you see it in science fiction a lot, planets with more than one sun, because people like to use that visual in science fiction movies and TV, because it looks so different. So is this the area that you want to stay researching? If you could study any mystery of the universe, what would you really want to know?
I think I find what I do really interesting, but I have been dipping my toe into astrobiology and kind of what is happening at the kind of planet level. So I'm really interested how planets can, how the Earth became, habitable, and the kind of processes that happen. So like volcanism is important, as well as, other things like obviously where you are around a star. And also the kind of the nature of the materials that you have, how much water you have, depends on the life that you grow on your planet. And so, yeah, I think it would be cool to investigate exoplanets a bit more. And in a way, it's kind of similar parallels to my current work, because, there are bodies orbiting other bodies, and I do a lot of that. So I think, yeah, I think that would be cool to investigate. And I think, yeah, looking into how you go from a hot kind of molten blob into something like the Earth, I think that's cool to investigate too.
Yeah, it is mind-boggling. We did a project working with the Science and Technology Facilities Council, that's my team, the National Space Academy, where we worked on their meteorite loan boxes, and we talked about the age of some of the rocks, and we had some young people holding them, and when you told them how old these rocks were, these space rocks, meteorites, it's just, you can't get your head around it. It's just I think one of the things that's really good these days is that data visualization, and when you showed those images that visualize things, it makes it easier for us to understand. Yeah. And that understanding it can be quite a challenge. So if someone wanted to be an astrophysicist, what would you say? Say if it's someone who's in school at the moment, in late primary school, early secondary school, what would you say is the best way forward for them? What should they be doing?
Well, yeah, I'd say I think in the UK, like, you have to keep studying science for a long time. So yeah, just keep doing that and keep working hard. But if you genuinely have an interest in astronomy, you can always do things at a young age. Like, maybe ask if you know someone who has a pair of binoculars. Can you borrow them? Can you use that to do some stargazing? Because you can already see so many wonderful things just with binoculars, not even like a big telescope. Like there's like star clusters you can see with just binoculars. You can and just loads of stuff, and meteor showers. You know, there's loads of lovely things to go out and have a look at. And so I'd say don't wait until you go to uni if you have an interest in astronomy. See what you can do. See if you have a local like stargazing club. Just get involved. And yeah, just try hard at your physics and maths classes, because you have to study maths if you want to do physics at uni, and to be an astrophysicist you have to study physics at uni. So yeah, but I would just say get out there and get involved. Like there's many great outreach things happening. There's so many lecture series for the public at different universities or schools. So just yeah, go out there, find get learning, because like there's so much fun stuff to explore, and if you are a young student, you don't have to wait until you go to university to start learning about astrophysics. And also check out so many books. Like there's loads of great stuff out there as well. Yeah, it'd be great.
I think that's such good advice, because I think sometimes when you are young, you think, oh, I've got to do what I've got to learn in school, and you almost feel like you need permission sometimes to follow your interests outside of school. So to hear from you, like a real life astrophysicist, that if you're interested in it, get reading about it outside of school time, and actually go and do some observing as well. And maybe there might be astronomical societies in your area, lots of universities, as you say, doing stuff online. And we've had a follow-up question from Casey. She's the one who asked earlier about how competitive is the field of astrophysics. And I'm interested to get your perspective on this. We hear a lot about gender imbalance in science. So the idea that physics is male dominated. Is that true in astrophysics? And what's been your experience as a female astrophysicist?
Okay, yeah, this is a good question. Unfortunately, there is a gender imbalance in physics, and that does trickle down to astrophysics as well. I think I was quite lucky when I was doing my PhD, because at some point we had basically half and half male and female astrophysics PhD students, which was great. But I think generally it is more imbalanced, and I think that's a shame, but it shouldn't put you off. I think it's nice when you have more. It's nice as a woman researcher when you have more women around. Like it's just we like hanging out with people who understand our experiences. It's just how we are. But it hasn't kind of diluted my passion for the subject, and I don't let worries about that hold you back, because I mean the only way that we can have more balance in the field is if more people want to do it. So don't let it dissuade you, I think, is my main point. Like, yes, there's an imbalance. Is it getting better? Yes. And I think either way, you are able to have a very nice time doing research in astrophysics. I've certainly enjoyed my journey, and yeah, while it can be a bit annoying sometimes, I think don't let it put you off, because if you're interested in the subject, you deserve to study the subject. So
that's a brilliant way to put it. And I'm gonna guess, would you say you feel the same about being a Black astrophysicist in a field that's majority white? Is that fair to say?
Yeah, I think again, it's annoying growing up and not seeing people like you in something you want to do. But if you have the passion for it and you want to do it, you can be that person and you can do it. So don't let, because historically the reason for this imbalance has been institutionalized discrimination, and that's why we are dealing with this imbalance, right? So it's got nothing to do with you as a person or your ability. It's got nothing to do with the fact that anyone is better than astrophysics than anyone else, because that is just not true. It's just it's about passion, it's about hard work, and it's about wanting to do it. So don't feel like just because you can't see a place for you doesn't mean that place isn't waiting for you. So just go out there and do it if you want.
I love that. That is such a positive kind of go-getting way to think about it, and you've obviously applied that in your own career, Abigail, to say, like you said, not necessarily seeing people like you when you were younger, but now you're actually being that person by agreeing to come and do some things like this. So we really appreciate it. And I wish you all the best with your studies over in Belgium and wherever in the world you might end up next, because I feel like you might hop around to a few different places. And when the National Space Centre is open next time you're back in the UK, you're very welcome to come to Leicester. We'd love to have you come and have a look at maybe some of our star exhibits and see if they match up to the latest science. So we've come to the end of our time, and really great to end on that really positive note. If you are interested in astrophysics, astronomy, you can find a way to do it. Make sure you study your maths and your physics. So we have a number of other takeover Q&As happening this week. Have a look at the National Space Centre's website and social media to find out about them. Massive thanks to Dr. Abigail Frost for joining us and putting up with all of my questions and my stunnedness about the multiple star systems. You can get in touch with the National Space Academy on Twitter, which is @UK Space Academy, or you can go to our website, nationalspaceacademy.org, to find a form where you can contact us if you would like to. Send us your space careers questions, and we may be able to ask them to other guests later in the week. And if you've got questions that are more related to the Space Centre, we'll pass those on to colleagues as well. Thank you once again, Abigail, and yeah, just excited to see where your research leads you to next. Brilliant.
Well, thank you so much for having me. It's been great to chat.
I know I could have asked you questions for ages, but I will let you go back to your work now. Goodbye, everyone. We'll see you at 5:30 for the next Q&A.